Okay, welcome everyone. Before I start with today's topic, let me remind you about a question we had Jürgen asked, I think, maybe 2 weeks ago or so, when I said that if the category of modules over Hopf algebra is pivotal, then the pivotal structure pi gives us a pivot for H, so that should be an element in H. And I already there said it should be pi H and not pi applied to the unit of H. And this gives, of course, an element in the double dual. But since we assume, and do not recall when I actually said this explicitly, but in that context, H was finite dimensional, and then the double dual is canonically isomorphic to H. And with that identification, you're getting an element in H. So for now today, the topic is, as I announced, different from in spirit from what we have been doing so far. I will talk about one application of categories that I think is important, monoidal categories, mainly modular fusion categories, but various aspects are more general. And this is in the calculation or description of correlators in two-dimensional conformal field theory. And this will involve various ingredients, which I will not fully explain, but I will try to explain quite a bit of what is behind and what we did not yet have. So it's written for which I call conformal field theory. And section 4.1 is generalities. 4.1. I do not write definition now most of the time because some of the things I introduce can be taken as definition, but unlike in mathematics, in physics, typically there is no full agreement on what the right definition of something should be, and these things change over time. But in any case, for me, if I say conformal field theory, it will be SCFT. This is a conformal quantum field theory, some people say, but I don't write this out. One reason being that in a certain part of physics, when you say quantum field theory, it means something formulated in Minkowski space. And that's not the case for what I will do. This will be in 2 dimensions. And conformal here refers to that we consider models which are defined in some way on a manifold that has a conformal structure. Conformal structure, by definition, is an equivalence class with respect to local rescalings of metrics. And you do not really use those metrics, but you remember a little bit about it. In particular, we are now in 2 dimensions, so this could either be 2 plus 0 Euclidean signature or 1 plus 1 Minkowskian signature. And what we also assume is that on those spaces, on those manifolds which we consider, which I will refer to with the physics word worldsheet, that this is also compact. One often works with non-compact surfaces, but at least one pretends to do so. But if something is really calculated, at some point one compactifies actually. And now, if I would have signature 1, 1, it turns out that the Euler number is an obstruction to the existence of a Minkowski metric. on a compact surface, and therefore we would only would allow for genus equal to 1, so for torus, and that's not what we want to do. So for us, this will also always be Euclidean, and you have to be aware of that in situations where you apply this in physics, the situation where you have one space and one time dimension. In that case, it's non-compact. At least time dimension is preferably not compact. Otherwise, you get into various troubles. But then you have to argue with it, and I will not try to do that. Now, the advantage of this is that you have various tools from complex geometry at your disposal. I will not use them very explicitly, but implicitly. The point is that if you have an orientable surface, then which has a conformal structure, then the conformal structure together with choice of orientation gives you a complex. Maybe I don't write that down. Now, an important aspect related to this is the following distinction between two types of conformity theory. One has to be very clear about that. There's something called chiral conformal field theory. And this should not be mixed up with what is called full conformal field theory. And I will now explain what that means. But let me first mention that until, say, 2 decades ago, people often were not very clear about which of the two variants they were talking about, and sometimes this leads to problems. Nowadays, this is very well established, but this doesn't prevent people still from sometimes mixing up things. So one has to be careful when we use the term conformal field theory. And the point here is that this is defined on a complex manifold. So 2 real dimensions mean 1 complex dimension. So one says on a complex curve. And it's captured by the theory of vertex operator algebras, representations or modules over vertex operator algebras, and by what is called conformal blocks. And about all of this, I will say something, but probably far too little to make you really familiar with that. But what I mainly will talk about, want to talk about, is full conformal field theory. And this is defined on a conformal surface. So 2 real dimensions and a conformal structure. And this allows, in particular, that it has a boundary. And also that you allow for defects. Defect lines are kind of internal boundaries. I will say much more about them later. And also possibly unoriented. The complex surface automatically comes with an orientation. Here we could have an orientable manifold, but choose to ignore that. But it could also be a non-orientable manifold, like a Möbius strip or blind block. And I should mention also that in papers, in particular by Jürgen Fuchs and collaborators, they look also at chiral conformal field theories where you have boundaries, or maybe not, but in any case, defects. But I cannot say anything about that. This lecture. Now, course 3 is about the connection between these two variants, and this is that for those full conformal field theories one understands, there is a corresponding chiral conformal field theory. So this is we continue here based on an underlying chiral CFD. And these conformal blocks form certain vector bundles, in particular vector spaces, over a given point in the relevant modular space, which I will call BL of well, all the relevant information that we will need, and then here these are sometimes called correlators. But that's not a good physical term, because when you say correlator, or in particular correlation function, you mean a function which is single valued, whereas you get these vector spaces, really spaces of solutions to differential equations, and they form as functions, they are multi-valued. But it may be possible to find single value combinations or single specific elements of those vector spaces, which are in some relevant space of conformal blocks. And to make this precise, it will take some time. Maybe at the moment I don't say more about this. We also have to specify some other aspects of what we want to call conformal field theory for there are many conformal field theories of either type, but depending on additional properties they have, a lot is known of them, or maybe less. And the most important class is the class of rational CFDs, or abbreviated as RCFT. So I have the vertex operator var algebra V. The representations give us a category of modules. Not necessarily, there is a notion of module, which I will mention a bit later, but we do not necessarily take all of them, but there might be some additional requirements. But anyhow, there will be some category V-mod, which in particular is a monoidal category, and I will just call it C. Before, and rational CFT means that C is a modular fusion category. So remember, modular means that the linear product of C with reverse grading is equivalent to the center of C, and fusion means that it's in a different symmetry. So one aspect in this is that indeed this is the in-particular category. So from the theory of vertex operator algebra representations, it follows in this case at least that this category C is a written category. Then there are what is for lack of a better name, called logarithmic CFTs. In this case, one has still a modular tensor category, but not semi-simple. So a better word for that is, remember, this means that I have what I call the finite tensor category. So a better name for this is finite conformal field series, even though this is also not a good name. MFC. Yes. And here there's modular tensor. Here. And then there are conformal field series which are not finite. The simplest one are still called logarithmic, and therefore this is not a good name here. For those who know what that means, the standard example is the 2,3 triplet linear model. And in that case, you still have some aspect of a modular tensor category, namely that there is a finite number of isomorphism classes of simple objects. But beyond that, there are other theories, including important ones which are known as uncompactified free boson and as the avail theory. These are more complicated. And for those, at the moment, I would claim one does not know what the relevant categories are. And I don't have to say anything about those. I will today mainly talk about rational conformal field theories, but also make statements about other finite conformal field theories. And one thing what you might have asked is, I have described here first what I mean by a full conformal field theory, and then just said where I get them from some underlying chiral conformal field theory. You could ask why, or are there full conformal field theories which do not come from a chiral conformal field theory? I cannot exclude that, but it's just not, there's no example known, and it's not even, I mean, if you think about it, it's very hard to come up with any idea on what that could be if it exists. So for today, I will take this as being one of the defining parts of full conformal field theory. Another remark maybe is that full CFTs can, oh, I should not write it like that. Some full CFTs can be formulated in terms of a classical Lagrangian. So this is a setting of quantum field theory which is used in many applications. So you would have some classical theory which is defined by Lagrangian, and then you have the corresponding quantum theory which is based on that Lagrangian and say some path integral formalism. In all of those constructions that I will present today, to my knowledge, this is not of any help. There are two important, well, there's one important class, so-called Wesselminer-Witten models, where the name comes from the fact that it's a two-dimensional sigma model with Wesselminer term, and the second W stands for Witten, who formulated these in the, as a Lagrangian field theory. But everything that is known about them from the Lagrangian point of view is also known from algebraic or the categorical point of view, but much more is known. And I could give you some examples, but I will not do not want to go into detail here. And there is a larger class, so-called coset models, which are built from the simulated models. And there are people who think of those models being defined really in terms of classical Lagrangians, and that this gives you all the information you can have about those models. But I would claim that without knowing the algebraic description, it would be very hard to, maybe impossible to derive those results. So, for example, what the field content is, which I cannot define right now, but which hopefully at the end of the lecture you know what it is. So now section 4.2. This is about chiral conformal field theory, and I write explicitly about chiral CFT because I, as I said, will not have time to really define things. And the first aspect of this is to say something about vertex operator algebras. This is not subject of the course. This is algebra, some part of algebra and part of category theory. So let me give here some references. Partly they are already in the list. Partly they will be added. Maybe those are all. So this is first Huang, Lipovsky, Gang. The one that is in the list or will be in the list, I think it is, but also other further papers by those. And then there is the book by Frenkel Benzi. And let me mention, when it comes to representations, the paper in the list by Kreuzig, Canada, and McRae. I think he's now. So you can ask him about the details. So what is this? There are the following basic data. I said I call this V. So V is a complex vector space. And in all interesting situations, it will be infinite dimensional. Then there is a linear map, which I call Y. Many people call this Y, from the algebraic tensor product of V with itself to Laurent polynomials in some formal variable, which I denote by Z, with values in V. So, and this means that these are a power series in Z and Z inverse, which are bounded from below, but powers are bounded. But there is a notation for that, which is maybe misleading, but which is very nice. Namely, one writes Y of A Z applied to B. This defines via this Laurent series the following. So here A and B are vectors in V. They correspond to the two copies here. Z is the formal variable, which I do not, by the way, indicate.
Which B is that? Y,
No, it's like that.
okay.
So Y here does not depend in any way on some variable set, but we use a formal variable in its definition, and therefore we write it here. So we mention the name of the formal variable, and A and B are in the vertex algebra, so this one would really write as y of A and B, as you say, with some reminder about that. But this is the notation people are using. I do not want to defend it, but everyone is using it. It will be hard to change. And there are reasons for that, but I cannot I cannot give you a good reason not to do it. So, and the reason, well, one reason for that is I think of, so this is now an element in B again. One reason for using notation is that I take two different roles for the two factors here. This I take as an argument, and B is something I act on, which I take as a free variable. So if I leave out B, then I have these ANs, which are then endomorphisms. So I have here, one then writes Y just of A and Z as the sum of AN z to the power minus n minus 1, where AN is in end of V. So this whole thing here is in end of V, with where I have arbitrary power series in Z and Z inverse. And often one requires some extra conditions here, but in full generality, what you have. And
what is the relation between A and the coefficient A?
Well, the coefficient, these endomorphisms are defined by saying that Y of A and B for given B can be expanded in this way. It's just convenient then to work with these endomorphisms. But this is not something I will do in any way from now on. But I have to explain, I think, the notation a bit, so that if you look at papers talking about this, you can get some. And then there are so these are the data. For now, there is not more, but there will come some part which you could use as a datum, but I formulate it as one of the axioms. No, sorry. I will not specify the axioms in detail, but just morally, what you say is that this pair consisting of the vector space and this linear map is, in a suitable sense, a commutative associative algebra. And it's not really an algebra in the usual sense, because of this label n here. You can think of this as a multiplication, which depends on, well, not one multiplication, but infinitely many multiplications. Or another way to think about is to say a multiplication, which in addition depends on a formal variable. And so when you write these things out, then this looks complicated. And then this is one aspect, and then you have a derivation also. But if it were an ordinary algebra, you have something that corresponds to a derivation on an algebra, and something one calls conformal structure, but it's not conformal structure in the geometric sense. I will tell you what to some extent what it is. And then there is a bit more to say. Let me see about the time. I say this only in words. There is a particular vector called the vacuum vector, 0, which has the property that if this Y is sometimes called the field map. If I apply this to 0, then and act on any vector of A, then I get A. And Y of A and Z applied to the vacuum, I do it the other way around, is of the form A plus a power series which starts with Z to the power 1. And then conformal structure means that there is a particular vector omega in V, which, when I look at the corresponding field and expand this, and now in a slightly different way than before, namely I define LNs if the power here is set to the power, if I have power n minus n minus 2, then these endomorphisms Ln generate a representation of what is called a Hörl-Sohn algebra with a fixed value of the central charge. So much about vertex algebras themselves. Vertex operator algebras, even the terminology is not uniform. Some people call this a conformal vertex algebra.
What is omega?
Omega is some, so I require that there exists such an element. So this axiom is existence of such an element. A few remarks about representation of vertex algebras, and about that I might not even write any detail. So a representation consists of a vector space, complex vector space, and a field map YW, where YW is non-analog. This is a linear map from B tensor over C with W to W of what one writes set in round brackets, and this means arbitrary powers, arbitrary complex powers in principle. So this is something very general, but there are situations where only, let's say, integers up to some rational, adding some rational number, they can appear. And classifying such representations or modules is in general very hard, and therefore often one imposes additional restrictions, and even then it's hard. But in any case, there is a kind of one gets a monolithic structure on suitable classes of representations, which is called the fusion. Well, it goes via something called the fusion product, which is defined differently from tensor product over A for an algebra, but in spirit somewhat similar. And this is defined via linear maps from the tensor product over C of two such modules to let me see. Maybe I was too quick here. There is some additional restriction here, and I forgot about it. But now in this case, I allow really for arbitrary powers, and this one indicates by a curly bracket. And in addition, these are polynomials in some additional formal variable. This is a new formal variable, but it has the it is connected to the old one by the same way it would be for an ordinary double. And in suitable cases, the representations together with the fusion product and a twist and a braiding and a rigid structure give you a ribbon category. And there is a general idea on how to get the rigid structure. Namely, these are vector spaces. What I didn't have time to say is that because of the Virasoro algebra, because of the action of the Virasoro algebra on the vertex algebra, V comes with a natural integral grading Vn, and under and there's nice classes, essentially all that one really knows much about, where these graded subspaces here are finite dimensional, and then one can take the grade-wise dual just of vector space, and this gives you a candidate for a rigid duality. And in the case of rational theories and these finite logarithmic theories, it indeed gives you a rigid structure, but not in general. And in the case of these, the next larger class, the hope is that there is a definition, and that there are what is called C1 cofinite, under which this grade-wise dual still gives you a Lie structure. And this is one of the reasons people working in conformal field theory are interested in conformal. And in particular, there is a notion of a rational vertex algebra, vertex operator algebra. This, as I already said, means that C is a modular fusion category. And there is this is a result. So there's an independent definition, but the definition is tailored in such a way that you get this. So we should really, the more sensible definition would be it's a vertex operator algebra such that C is a modular fusion category, and then try to disentangle what this means for the vertex algebra. Then concerning modules, there is a concept called a character, analogous to characters of representation of Lie algebras. Yeah, just let me just write this and then. This is not known, I think, but there are people who believe it. When it comes to vertex operator algebras, I have no opinion at all. There is this quote of, I think it was Gelfand who in a talk where vertex operator algebras were introduced said, "I'm an old man and I know a definition cannot be so complicated." And then there is a paper by Victor Katz and collaborator, which give you, I think, 10 or more equivalent definitions of vertex algebra. And each of them I mean, they are all equivalent, but they look very different. So it's not in some sense a very natural structure, but I could have said this. This was developed in the first place by Borges from trying to understand what physicists have been doing in conformity, in either conformity. And it doesn't get much better than what it is now. Yeah, there's a notion of character. If I have a representation W or module W, then I introduce a formal parameter tau, formal in the first place, but as a trace of Q to the L0 minus C divided by 24, where L0 is the zero mode that I have in the expansion here, and C is the central charge. So that is really there is a central element which acts as a number C times the identity. And this Q is related to tau by e to the 2 pi I tau. And if I think of tau as a complex number, then under suitable conditions, these functions here converge in the upper half plane. And in the case of a rational vertex operator algebra, one knows that there is an action of the modular group as a percent, which sends I to chi at minus 1 over tau and tau plus 1, but you can define this in any case. But in the rational case, this gives a finite dimensional representation of SL2Z. And the matrices, then also called SNT that you have here, which are the generators of SL2Z, these are precisely the same as those you get from the category C in the way I defined some time ago. Now, this fact and a little bit more is also known as the Verlinde formula, and showing that these matrices that you get here are the same as these other matrices is actually complicated. Sometimes one says the Verlinde formula states that the S matrix diagonalizes the fusion rules. This is actually only a very small aspect. Namely, it said this can be reformulated by saying that the matrix S that you get as invariant as the number you get from the Hopf link, that this is the same as the matrix which diagonalizes the fusion rule matrices, and the proof of that is one line. Whereas the relation with here, this is complicated, and it has been obtained. Well, it has been. The proof has been given much later than after people had claimed this. So next part, still about chiral conformal field theory, are conformal blocks. And this is in the general spirit of what in quantum field theory one calls state field correspondence. So by state, one means a vector V in one of these modules, say W lambda. I will, when I label them, I will use this label lambda as I did for the situation where I have a semi-simple category, but it could also be just an arbitrary object in general. In the rational case, it's without loss of generality, a label for a simple field, and I want to associate to this some phi lambda, which depends not only on lambda, but also on this vector v, and in addition, on a point P on the worldsheet S. To which one? Well, on some manifold in our situation on the worldsheet, which I will denote by S. And this is called a field, and depending on your approach to quantum field theory, this can be a lot of things. What it is here, I will try to not explain, but anyhow use conformal blocks in a suitable way. And I'm already over time, but let me first let me still write something here. The aim is here that one assigns to oh, I should not write worldsheet because this I use for the full conformal field theory. Let me say here a complex curve and denote it by x. I assign to x and points p1, say to pm, finitely many on x, and to each of them a label lambda. Something some people call correlator, but I do not give it a name. You assume that there is some form of what people call an operator product of fields. So you can multiply them in some sense. And then associated with some function, or in fact multi-value function. And this then you call a conformal block, but there is also a more general definition, namely that, a more concrete definition, namely that due to the fact that I have representations of the vertex algebra, these fields carry some action of the vertex algebra, and as a consequence, these conformal blocks will carry certain actions, and these can be realized as differential equations. This is called word identities, and then you get these vector spaces of conformal blocks as solutions of differential equations. That's the only thing that really that will matter. And in the situation in rational conformal field theory, but also quite a bit beyond, this will be finite dimensional. Okay, now I should stop and then continue now. Maybe we wait. Oh, yeah.
So it does that.
No, we should continue, of course.
And what we should make a note here.
Oh. These fields here are some physical idea. One could think of them as what is also called fields in vertex theory, as these vertex operators Y, but they they depend on a vector in a module. That's fine. Y lambda 1, we have to put the W upstairs here. Well, W1 lambda 1 to be precise. But then we have some formal variable here, and we have to make a relation to the point. And the relation is that you can take a local holomorphic coordinate at that point, but you have to do this for all of these. So you will deal with different formal variables, and you have to be careful in manipulating them. And I have no intention to go in any detail about that. But you can do things in such a way that you indeed do not have to talk about the phi's here, but in a way using only the actual information you have in your mathematical theory to get to differential equations and to then look at the space of solutions. And I just want to indicate in one case how you can do this. In Westerminer-Witten, this is, I didn't say this, but I say it now, that C is the category which I call CGL before. So G is a finite dimensional simple Lie algebra, complex Lie algebra for us, and L is a non-negative integer, and there's a semi-simple generalization of that. And in this case, you define what is sometimes called a global Lie algebra for this situation. Namely, you take the tensor product over C with of G with what I call x f of xp. This is the space of functions which are meromorphic on x with poles at most at the points B and those at most of finite order. So this is an associative algebra, and tensoring with G will give you the algebra, and then you associate two. I write here J0 tensor F, where F is an element here, and J0, this is physics notation, it has some origin, a Lie algebra element. So this is an element here. I associate to this. I forgot to have some notation, but afterwards. For each value of I that I have for these labels pi and lambda I, an element which one calls ji of f, defined as sum over n ani jn, which is an element of the untwisted affine Lie algebra G1 associated to the finite dimensional Lie algebra G, where these ANIs are defined by taking a local coordinate, which I now call theta I, local holomorphic coordinate in the neighborhood of P1, such that when I expand my function f here in this coordinate, then I get these ANIs here as coefficients of the power n of the coordinate. So I have this algebra. I take an element this gives me these A and I's. These are elements. I get display elements of an affine algebra. The vertex algebra in this case is completely determined by this affine algebra, and therefore the action. Well, via this for all I get an action of m copies of the affine algebra on. I get an action of this V algebra on the tensor product of the vertex operator algebra representations, and then I can look at the invariance with respect to that action, and this gives me writing down what it means to look at invariance is a differential equation, and the solutions to that are these are called spaces of conformal blocks. And I will be noted by BL of X and P. And implicit, maybe if I want to make it explicit, I would write here an index lambda. So for it at position pi, I have representation labeled by lambda. Now, this works nicely for vestibular. And in fact, it's not hard to be more explicit about that. But if you want to do the same thing for other rational vertex operator algebras, you need an analog of this algebra. But because there is no underlying G, it's much harder to define something like that. And I will not say anything about this, but just mention that it has been shown that for rational conformal field theories, when you vary, you get finite dimensional vector spaces in this way, and when you vary the moduli of the curve X and the positions of these insertions of fields, then the various vector spaces you get are just the fibers of a vector bundle over the moduli space of curves with marked points. So in the vector bundle, I will indicate by a script BL. And this will depend then on the G, this is now genus of X and lambda on moduli space of curves with a given genus G and a certain number of marked points. This does not talk about the local coordinates. If I include them, then I get a much larger model, an infinite dimensional moduli space of curves with marked points together with local coordinates. One can show that in that case, one still has a quasi-coherent sheaf over that infinite dimensional moduli space. In the case that V is rational and what is called C2 cofinite, one proves that this, but that one gets more generality, but this defends then to a vector bundle really on this finite dimensional moduli space. And again, I cannot say anything more, but in particular, this means that this vector bundle comes with a projective action of the mapping class group of curves of genus G with nine points. And then when one talks about conformal blocks, sometimes one means concretely these vector bundles. Sometimes one means vector spaces for a given fiber. Sometimes one means this alone is not much, it's just a finite dimensional vector space, but a vector space together with an action of the mapping class group. Plus, actually, something which I have not yet talked about, that these bundles which I have individually for some curve X of arbitrary genus, that they are not independent. But if I look at the curve, which implicitly I assume when I said curve, it's a smooth curve. So it's smooth as a manifold. There are curves which have what is called an ordinary double point. So if you think it as a curve in just on the blackboard here, then this would be a double point, and ordinary means that just like this indicates, if you go in a direction, you can split this up into 2 points, and this has certain compatibility requirements. In particular, when you think of this now as a two-dimensional manifold, such a double point would, for example, correspond to the situation that you degenerate this here to something which has been a zero, but is connected. So these are there is then a corresponding notion of moduli space of stable curves, which are curves with such specific singularities. And you can show again in the rational case and possibly beyond that the conformal blocks give you actually a vector bundle on the space where the of stable curves with marked points. And this corresponds to having you can now look at what happens when you dissolve such a double point into two ordinary points, and this corresponds to that you have linear maps between the blocks for a given situation is two where this has a double point, which I do not indicate here because it's in X. To the direct sum of the spaces you get when you add to these points two more points, which carry labels mu and mu bar. So there's an X prime, which has not just the original insertion points, but also, let me call it P plus and P minus. So these are the 2 points you get from resolving your double point, your singularity. And these are called a sewing or factorization maps. And then when one says conformal blocks, one typically means, when one talks about vector spaces, one means finite dimensional vector spaces with an action of the mapping class group and coming with such. So a system of such spaces coming with such maps. And this is actually still One way to think of conformal blocks. A priori, completely different way is the following, and people are still using the same word conformal blocks for that. Some, some people call this topological conformal blocks. This is so here I use explicitly the representation theory of the vertex operator algebra. Now I just use the category C, not remembering where it comes from. And then I can define a block space, which now does not depend on a curve, but only on its genus, and not on these positions, simply as morphism space in C. Namely, the morphism space, I'm now using Y in the notation I had previously for the simple objects. So these correspond to the vertex algebra representation W, but just regarded as objects of my category. And then I have a tensor product. Previously, tensor products stood for tensor product over complex numbers. Here I now have the tensor product in C. And then tensor unit. So this is by definition a finite dimensional vector space, complex vector space. And this is actually true if the genus is 0. If I have higher genus, I have here to add a tensor with the genus tensor power of a certain object L, and this object L is defined as the direct sum over all lambda and lambda y lambda dual tensor y. And this corresponds, the presence of these corresponds to the fact that if I have a genus G surface, I can think of this as this corresponds to a curve with G double points. And if I resolve all of those double points, then I get these additional labels U and U bar, which is called are the labels. Maybe I should write mu here to make the correspondence clearer, and remember that the bar on the labels corresponds to taking the dual on the object. And at this point, it turns out that in this description, it's very easy to go beyond the assumption of a modular fusion category for an arbitrary modular tensor category. I can take the same definition, except that I recognize that this direct sum here is actually nothing but a way to write the coend. And in the general case, direct sum does not make sense anymore, but coend does make sense. So that one should not write X, write U. You get correct results by just taking this object. And notice that if C is semi-simple, then by definition of the coend, this here is the same, well, canonically isomorphic to this direct sum. So this concludes a full CFT. This concludes chiral CFT. And now I finally can come to full CFT. And as I said before, when I think about full CFD, there will be some underlying chiral theory. In this case, I also said that I have this two-dimensional manifold, which we call a worldsheet. But when I say worldsheet, which I denote by S, I mean this first as a manifold, but then also with possible additional structure like defect lines or such insertion points. And this will have an underlying pure manifold just, or manifold with boundary in general, which I denote by sigma S. So now what I want to do is to give a prescription how, based on the data that I have in the worldsheet, I can first identify a certain space of conformal blocks. And once I have done this, determine a specific vector in the space of conformal blocks, which has the property that it corresponds in the description of multi-valued function to a single valued function, so a horizontal section of the corresponding vector bundle. And that it's compatible with stowing in the sense that if I take correlators for two worldsheets and sew them together under these linear sewing maps that are provided by the chiral theory, these are mapped to the correlator of the sewn worldsheet. And there is one important additional ingredient that I need for being able to do that, namely that the chiral symmetries of a full conformal field theory are described not by a vertex algebra, but a pair of vertex algebras. Call them VL and VR for left and right, but at the moment this is just it is just a terminology. It comes from the particular conformal field theory of free bosons, where one talks about left and right movers as particular solutions of a differential equation. But this is not important for us. For us, it's only important that the category that we are talking about is or is equivalent to. We can often we will strictify the category of modules over the tensor product over C of each group. And then we can do this in general, but from now on, I will restrict to the situation that CL is some given C and CR is C ref. Maybe I have used C bar before. I don't check this out. So this is in the rational case, and analogously, you can do this in some more generality. In the rational case, this would be modular tensor category, so in particular braided. Modular fusion category, but in particular C is always braided, and C ref or C bar is the same underlying monoidal category, but with opposite braiding. And
what do you mean by that? What is C? What is C? You define VL?
Well, I just saw this. So I could have written CR as CL ref, but I just use C. And also recall modular, which I will assume can be defined by saying that the linear product of C with C ref is braided monoidal equivalent to the Greenfeld sample. Now I have to tell you still what ingredients I have in my worldsheet, which I denote by S. So there is first this manifold, compact, smooth manifold in general boundary. Which I call sigma S. Then I need something called boundary conditions. On part of the geometric boundary of this surface here. In which part of, I cannot explain yet, this will become clearer a bit further. Notice that in the description of sewing, in terms of manifolds, a picture one often sees is like that. So that means that I have a boundary circle here, which really comes from the fact that I have such an insertion point. This would be P plus and P minus in the notation I had, together with a local coordinate, which I also can describe by saying I have a parametrized disk, and I take this out, and then I have the corresponding boundary circle here. And this is called a gluing boundary. Or gluing boundary component, and it's part of is part of the boundary which is not gluing. Some people call this free boundaries, some people call this physical boundaries, some people call this end of the world boundaries. There are various names for that, but it's for us, we just partition the boundary in two parts. One are gluing boundaries that correspond to this situation here, and the rest, and those are parametrized. The not gluing boundaries or free boundaries will not be parameterized, but they have to carry a label. And this label is called the boundary condition. And for the moment, it's just a label, and I cannot say what it is. Well, not more about what it is, but in the last part, I will specify this in the case of, well, in various cases. And then there can also be, as I mentioned, defect lines. To be precise, topological defect lines. This means the following. Our aim is to determine the correlators, which are special elements in space of conformal blocks. And on my geometric surface sigma S, I am now allowed to have such lines, and topological means that the correlator, the specific element I'm talking about, will actually not depend on these on the precise position, but I'm allowed to vary that as long as I do not touch any other relevant information. So I cannot cross another line, and also if there is a field insertion about which I will have to talk, then I'm not allowed to cross that. And again, this is a line with associated, just like here, boundary condition. One sometimes says defect condition, which again is for now just a label, some label. And then there are field insertions. And these correspond to these fields I have now defined, phi lambda of P, which correspond in a fluid sense to the field operators or vertex operators in the chiral now in either of these parts or in both of them of the vertex operator algebra. And there are actually previously I had a complex curve, so this corresponds to the situation that I have one of these algebras. Now I have two, and two of them are relevant if I have an insertion somewhere in the interior here, and those I will denote by phi. If there is no defect line, if they lie on a defect line, I will use it. There's a theta instead, but I can have a free boundary here, free boundary component, and there might be a circle here, which partly is free, but on a free boundary, I can have what is called a boundary field. And that I will denote by psi. And psi will actually, I take this way away. Psi will depend on, well, I need, I call boundary conditions M for some reason. So if I have such a field insertion here, then on one side along the boundary, there will be boundary condition M, on the other side, a boundary condition M prime, and this will depend on them. And in addition, it will depend on an object in the category C. So let me write this as golden degree of C. And then there can be defect fields, which I denote by theta. And they depend on two labels in C, or in golden degree of C. And they depend on two defect labels, which I will denote by D. So if I have an insertion here, on one side I will have a defect condition D, on the other side a condition D prime. And in particular, as a special case of this, I have what is called bulk fields. For those, there is just no defect line, or one can also say there is a defect line, but it's invisible. It turns out that these labels here are actually the objects of a monoidal category. This monoidal category has a unit, therefore D equals 1 is one possibility here. And if I take D equals 1, this corresponds to, according to the graphic, analogously as in the graphical calculus, not seeing it, and therefore we have a situation like this here. And those are especially then denoted by D phi, and they just have two of these chiral labels. Now, I talk here about points. We still have to remember to some extent that we are not dealing with vector spaces, but really with fibers of some vector bundle. So and they come not only from the positions, but also from this large moduli space where I have local coordinates. And a little bit of that we have to remember. And one way to do that is to say that actually we cut out a little disk here. And this is then describes our field insertion. This fits nicely with the graphical calculus when we would think of this as a coupon, which is labeled biomorphism. We'll come to that. Another possibility is to say that instead of cutting out a disk, we remember part of the local coordinate by having a germ of arcs through the point. And this will become relevant when we extend this to 3 dimensions, which I will need in a construction later on. If we do this by taking out this, then from such a circle that I will get some tube. Whereas if I have described in terms of an arc, I will get a ribbon. So, but in any case, not just a line, but or a line with framing. And now there are various ways to try to say what I mean by a full conformal field theory based on a chiral theory with monoidal category C. Somehow it has to account for all these possible types of data. And one way to do that is, and you can take this if you like as a definition, but I will not indicate it formally as a definition. I say that a full CFT based on a chiral theory with category C is a consistent system of correlators by which I mean an assignment I take a worldsheet S with all these possible ingredients and associate to it something I call the correlator based on C for S, which is an element in a suitable block space. Let me call it C of S. This is a new notation because I still have to relate this to the spaces of blocks that I have introduced before, such that this is these vectors I get here are invariant under the mapping class group action on the relevant one, which again I cannot maybe let me write map of S again, not yet defined, and which are compatible with sewing in the sense that I already mentioned. And then one can show I should have mentioned for conformal blocks. If you want to know something about conformal blocks beyond Witten, then look. One possible way is to look at the paper by Damiolini and collaborators, and also for a very brief review, there is a review paper by myself and Christoph Schweigert and Simon Wood and Johann. You also find the list. So there is the following result, and for that is again with Christoph Schweigert and Ingo Runke, but also with Jens Fjellstad. The following statement for C, modular fusion category. Under certain mild assumptions, we just write non-degeneracy here. Non-degeneracy assumption. Namely, these differential equations are linear differential equations. So a solution is to take all correlators equal to 0, and that you want to exclude. If you exclude that, then you have the following. There is a bijection between full CFTs based on C, full CFT in this sense, and Morita classes of SSS FAs in C, where this here stands for Frobenius algebra. We have defined this last week. S here stands for simple. Simple means not in the traditional sense, but simple as a bimodule over itself. It was important that we can think of an algebra as a bimodule. And then here, this stands for special, and this stands for symmetric. And I have not defined them, but it's very easy to do that graphically. A special means that, remember, Frobenius algebra has a co-product and a product, and I require this identity, and also that co-unit after unit, which is an element in the endomorphisms of the tensor unit. So it's a number, that this number is not 0. And symmetric means if I take the definition of Frobenius in terms of this invariant non-degenerate form, that, remember, we have in particular a pivotal structure in our category, that I have this identity. And then I need, so if I have X here, A here, then I would have a double dual, and I put the pivotal structure. And the proof is, well, it has two parts. In one direction, in this direction is, if I take such a Frobenius algebra, I will get a consistent system of correlators, and I can show that the result is invariant or in a way covariant under change of representative in the Morita class. And the other direction is a bit more complicated, and I will actually not say anything about it except that invariance of a mapping class group action is easy to show, whereas the solving part is much more tricky. Again, I'm over time. Let me just mention one more thing. I should have added here on-oriented worksheets. If I allow for unoriented, even non-oriented worksheets, then I have to add a little bit here. And it's also known what, but I will know. Okay, let's have a break, and then after a small further comment, I will give you the construction, starting from such a Frobenius algebra getting a consistent system. To continue, short remark, such a Morita class of algebras in general is equivalent to specify module category over C that we have mentioned. That these are not just arbitrary algebras, but of such particular type. Actually, it's not a very strong restriction. If I in many cases, if I identify an object in the category in algebra structure, there is a very good chance that it is special symmetric Frobenius, not necessarily simple, but every algebra is a direct sum simple algebra. So it can control that aspect. Then it was I have to change number. It should have been 427. And now 429 is about a partial role of, if I call the algebra A here. And the first is that boundary conditions. Remember, up to now, this was just the label M. It turns out a boundary condition is nothing but an object in the category of A modules and say right modules. It doesn't really, it's not really important. And then concerning boundary fields, remember they were of the type, I specify two boundary conditions and a label in the in C. Let me write here just an arbitrary object U. Then this corresponds, well, the space of these fields corresponds to the space of A module morphisms from U tensor M to M prime, where U tensor M has a natural right action via M being a module. And continuing with this, if I have the situation that I have a defect line, remember for a priori, this was just carrying a defect condition D. This is a bimodule where if I have a defect line on the worldsheet, then actually on one part I will have a full conformal field theory based on algebra A. On the other side, it will be some other full conformal field theory A prime. And then this is an element just of the category of A prime bimodules in C, and then a defect field theta E prime. Now I have two correlators U and V. This corresponds to a morphism space, morphism of A prime bimodule morphisms from roughly D to D prime. But I also have to account for U and for V via tensor product. Now this would not work because I need a bimodule, A prime bimodule structure on this. But there is a way of using the braiding, which I indicate by this subscript plus and minus here, under braiding, to make this object here into a bimodule. And this is implicit now in the way of going from, well, not a Morita class, but some representative of it to prescribing what the correlators are. This is for 4. This is called the TFT construction of correlators of a full rational conformity theory. And the first observation here is that, let me write, of RCFT correlators. First observation here is that if I have trial RCFT, this corresponds to a modular fusion category C, but also it is known that the modular fusion category C is the input in a reciprocal into a three-dimensional topological field theory. And I will not tell you what that is. Probably you know that anyhow. But the important thing is that in a three-dimensional topological field theory, you assign finite dimensional vector spaces to surfaces and linear maps between those vector spaces to three manifolds, which have the surfaces as boundary, and the surfaces can have marked points or arcs, and the corresponding three manifold will then involve ribbons ending at those arcs, and ribbon graphs ending on those arcs. And the idea is now to think of a correlator of the full RCFT for a given modular fusion category C as a specific vector in a TFT state space. And what we are doing here is that we silently identify these finite dimensional vector spaces in topological field theory with conformal block spaces. And there is something to be said about this. There is some assumption here, but I will not go into this today, but mention a little bit about that next week, on Thursday and past part. But we accept that. So the TFT space is a space of conformal blocks. Now, if this idea works, then we have to do. We can proceed in several steps. First, we have to identify what is given a worldsheet S, what is the relevant space of conformal blocks, and then have an idea on how to specify a vector in such a space. And if you have the general idea, then make that idea more concrete to give a brief description. And so let me just mention here that if we have, the idea continued would be more concretely find a three manifold M S, meaning that given the worldsheet, I can tell what the three manifold is with embedded ribbon graph and define the correlator for S. S, I call this TFT just said, a letter that is often not used for this, and I will silently suppress the label C. So I take Z of M. By definition, this is MS. Is by definition a linear map, and now linear map here is always between two vector spaces, one associated to what is called the incoming boundary and the other the outgoing boundary. I take the incoming boundary to be empty, so everything outgoing. So MS will be DMS will be the empty set. And I'm using the fact that set of the empty set as a two-manifold. It's just complex numbers. So this is a map from the complex numbers to a certain vector space, and I can apply it to the number 1 in the complex numbers, and I will get an element in the vector space. And if the vector space is the space of relevant space of conformal blocks, then I have identified a particular element in every space of conformal blocks.
So MS should be a two-dimensional manifold.
S, well, remember S is the word here. It involves the two-manifold which I call sigma S, but also the additional information about boundary conditions, defect conditions, and field insertions. And MS will not only depend on the geometric information, but also on this. So that's actually I mix up my numbering. Instead of 33, I continue with 23. That's me. I will follow that here because I will not be able to go to keep adding 10 all those numbers. It's far too complicated. So I write 423, which is really 433, now I try to do this to how to specify M sigma, MS. And in particular, there will be sigma S. I noticed that on sigma S, I will have insertion points. I continue now. I will talk about points. Really small disks removed or small chunks of arcs. But I have this, and in the case of a bulk field or a defect field, I have two labels from C, but C is relevant here for the topological field theory, so I need somehow two copies of that, and I implement this by saying that I have two points, two labeled points on the boundary of my three-manifold. Remember, the boundary is relevant for the I said it in words, but I didn't write it. The in boundary is empty, and the out boundary is where the insertions will be. If I have instead a boundary field, and there is only one label from C, and therefore there should be only one label point on dm sigma ms. And if you think about this, then you get the following prescription that you want the boundary of MS. So we do not know yet what MS is, but its boundary should be what is called the double or complex double of sigma S. Namely, this you can define as OR of sigma S. This is the orientation bundle over sigma S. So this is nothing but the sigma S times a minus 1, 1. The 2 points, but divided out by an equivalence relation, which says that a point P with an orientation, given orientation is the same as the point P with the opposite orientation if P is in the boundary of sigma s. Example, take a disk. Then over each interior point of the disk, you will have get 2 points, but over each boundary point, you will get 1, and you can easily convince yourself that this gives you a sphere. Also, if there are no boundaries and the surface is orientable, then sigma s hat is just 2 disjoint position of the copies. So now we know what the boundary is. What can we say about the 3 manifold? First, not thinking about the Jürgen graph in it. Well, essentially, we do not want to introduce any new global information. And it means that it should not be an arbitrary 3 manifold, but you could say it's just a thickening of the 2 manifold we start with. But not just a thickening, this would be 2 manifold times an interval, but you have to account for this identification or boundary point. And if you again think about the possibilities here, then you can see that the sensible definition is that you take sigma hat s times an interval, and you divide out an equivalence relation, which is of the form that if you have t, so t is in the interval here with a given orientation of a point here that you identify this with minus t and minus the orientation. You could actually just say you take sigma s here and have another relation as long as sigma s is orientable. But if it's not, if it's unorientable, then this is a bit preferred. And again, in the case of the sphere, what do you get? Well, you have to think a bit about this identification, but what you get is a 3-ball, which has the sphere as boundary. And also, if you maybe I will write this separately. Simplest example. If sigma s is oriented and it has empty boundary, then ms is nothing but sigma s times interval. Or the identification then just removes 1 copy of at least 2. And this gives this as a manifold, but you still have to specify the Jürgen graph. And what is clear is that the Jürgen graph has to end on, if I talk about ribbons and not tubes, will end on small arcs corresponding to the insertion points. And then in between, there should be as little information as possible. And it's no longer there. The information comes from in what vector space to what vector space the field insertions correspond. And let me not give this as a general definition, but make it clear in the example of, let's say, a disk. So we have here S equals, for the moment, a disk, but with additional ingredients. Then we know that sigma S hat is a 2C. If we have a field insertion on the disk, which is a bulk field, it corresponds to a small arc here, and there will be a corresponding small. There will be two corresponding arcs here. So we will have a ribbon, which somehow should be connected to this. And the prescription is now the following. Remember the space that we assign here was, I wrote it only for defect fields, but the special case for a bulk field is that we have bimodule morphisms where A prime is equal to A, and then the defect field at the defect label B is actually the tensor unit, which is in the bimodules A itself. So we have from AA U tensor plus A tensor minus AA. So let's use blue for A. We'll also need a ribbon A labeled A incoming, and then we have some coupon here and A outgoing. And these lines here, if I have U and V for my chiral labels, one of them will be labeled by U or V, except that maybe it's a dual. All these ribbons are, of course, the corresponding lines are oriented, and I do not indicate orientations here. If you do this carefully, it corresponds to what I have here. And I still have to tell what happens with these A lines, and for the moment, that's all I need and all I want to say. But this is for a bulk field. Analogously, if defect field maybe I take it later. Let me make this a little bit larger here. What happens with a boundary field? Well, if you have a boundary field that corresponds to a small arc here, then there is only one arc on the on this surface here, and you should again connect this somehow. But again, if you remember how I described the space of boundary fields, this was a module morphism where there was another chiral label, which was U, and there was the M, which is the boundary condition. So I have more colors. Let me take this also in blue. So there is a boundary condition M here, the boundary condition N prime here, and then there was morphism where I have an A line. Now here, this is I have a whole space of such morphisms, and also here. So in order to make sense of it, I have to choose one element or a generic element. Before coming to defect fields, let me also tell you what happens with these dangling A lines. part of the prescription is that I put what I call the full frobenius graph on the worldsheet. So I now just draw lines, but these are all ribbons. So there should be a graph, possibly with one valent vertices, otherwise 3 valent vertices, where the vertices are labeled by multiplication, co-multiplication, unit, and co-unit, according to orientations, which again I suppress. But then this is also connected here to the boundary. And if there is a boundary condition M here, and I connect it here, and then this is not an arbitrary morphism, but it's the representation morphism. If I do orientations correctly. And now the generalization to defect fields, where I have here A prime. Sorry, this was not A, this was a. Instead of A, I have then D, and I have D prime. I draw this separately. So instead of having an A line coming in and A line coming out, now I have a line D and D prime coming in and out. And here I have U and V. And now I can explain what this plus and minus means. These are objects. D is a bimodule. So an A prime bimodule. So I can act, say, from one side with A and from the other side with A prime. But I want to act on the tensor product here. And that I do by using the braiding. And in one case, I use over braiding, in the other case, under braiding. And now the red lines are now the A's and A primes. The red and blue lines lie horizontally here in the worldsheet. I forgot. You can show the worldsheet is always embedded as a deformation retract in this manifold M. So this picture really makes sense geometrically. This here means that well, depending on my conventional, the U line here, maybe I do it here. Prefer a bit the other way around. The U line will be above the A line, so it will be in the upper half sphere here, half wall, and the V line will be in the lower one, as I drawn it here. And in this way, you specify a ribbon graph, and that's really everything you now need. And now let's remember our prescription for the correlator. I'm not sure, maybe I forgot to write it down in my notes. The block space for S is the space of conformal blocks now for this sigma hat S, where if I have labels, well, the representation labels, these give me the representation labels here. But no, so if I have here n bulk or defect fields and m boundary fields, and this will have 2n plus m mark points, labeled mark points. And I think I think of the space of blocks in terms of these categorical or topological conformal blocks. So these are just morphism spaces. And now remember, I said that the correlator for the worldsheet S is defined as the Reshetin-Torayev topological field theory based on C for this three-manifold S with embedded ribbon graph applied to the number 1 in the complex numbers. And this is, by definition, an element in the space, in the TFT space, state space, corresponding to the boundary. So in the space of blocks that I'm considering. This is something which makes sense. It specifies a correlator, and then the statement is that, as I have formulated before, doing so gives you a consistent system of correlators. So correlators defined in this way for all possible worldsheets S are compatible with Zoe, and they are invariant under mapping class groups. Now I have to say which mapping class group. The mapping class group, if there are no defects, it's just the mapping class group of sigma S. If there are defects, I have to require that I only look at subgroup which leaves the defects invariant up to small deformations. So it leaves the topological information in the invariant. And theorem then is this indeed works. And in the paper I will reference this. This is paper 1 in the series. This gives some basic ideas and some examples which I will tell you now, and then this goes up to paper 5, where paper 5 has the proof that of the theory. And then there's a separate paper which is the other direction, namely that every full conformal field theory based on the chiral conformal field theory, category C, rational conformal field theory, is of this type. And let me yes, I think I can present a few examples. The first example is essentially already on the blackboard. I take a disk with just one bulk here. So this simplifies the picture here to there is then only one boundary condition M. And also remember, I said this has to be a full Frobenius graph. Full Frobenius graph means an arbitrary one. One has to show that here one makes many choices. One of them is the choice of full Frobenius graph. The result you get is independent. That to show. And that means in particular you can take the simplest full Frobenius graph. Namely, this is just the one where you have a co-unit here and just a line with a representation morphism here. And then correlator for this case is this. To be precise, it's Z C of this three manifold applied to the number 1 in the complex numbers. Now, this is the end result, but you might not like it because it's not explicit enough. So we can make it more explicit by expanding it in a standard basis, provided there is a standard basis. Otherwise, you take some basis. But in this case, there is a standard basis, namely a basis of the relevant space of conformal blocks. These are 2-point conformal blocks on the sphere. So you have a sphere, and you have 2 points, or arcs, that we get ribbons, but let me just split this as points, and I have a label, and this is labeled by some lambda. And instead of having u and v, I take simple labels, mu and mu prime. And how do I get, so I can expand this as a linear combination of these for all lambda and lambda. How do I get this? I evaluate them on the dual basis. The dual basis is the same picture, but now not regarding this as the boundary of this interior ball, but boundary of the exterior ball within S3. So you glue this, you take this 3 ball and glue it to that 3 ball. You get thereby an S3. And if you have a ribbon graph in S3, restricting to arrive tells you project that ribbon graph to the plane in a non-degenerate way. And the resulting picture you take as a morphism in your category. So what you get is that the correlator is the sum over all lambda. And then you have a delta lambda mu prime, because this lambda must fit here and also there. And then you get in S3, you get a ribbon graph where you have 1 ribbon labeled by lambda. Again, I suppress orientations. 1 ribbon labeled by m. And then, in addition, you connect them by a ribbon labeled by a, where here you have the representation morphism, and here you have a morphism which is part of the data, namely which part of it you have. Special case. There is always the algebra tensor unit, which is in particular simple special symmetric Frobenius algebra. If you do that, just the A line becomes invisible, and you just get a Hopf link. The invariant of the Hopf link up to a number is this modular S matrix. And if this is 1, then the labels for the modules are the same as the Farrell labels. So we get really S matrix. And this is a well-known result. And this generalizes naturally to these numbers. You can also show these numbers have the meaning of the elements of the modular matrix for 1-point blocks in the torus rather than 0-point blocks. But to explain that would need more time. We're not able to do that. Instead, I will describe 2 more examples, which are very special, namely without any field insertions at all. But for some purposes, these are, in fact, the most important ones. And one of the most important ones is the torus. And the correlation function with no insertions is also called in physics partition function. So what do I get here? Let's think of the torus as a rectangle with identified opposite sides. And now I don't have any correlators now. So the only thing I need is a full Frobenius graph, and a possible full Frobenius graph is, it should be, looks like that, where these points here are identified, and here say I have the co-multiplication and here the multiplication, depending on my choices orientations. So this is the graph that you get on the torus. Now the three manifold in that case, because there is no boundary and it's orientable, simply M S is my torus T times an interval. So where the worldsheet is embedded at the middle, say at coordinate value 0. And then you see that the correlator in this case can be described as follows. The interval times the torus I draw in the following way. I take a full torus, so a cylinder with identified top and bottom, with a small full torus cut out. And then I have a graph labeled by the Frobenius algebra A, which roughly looks like this. Then I have a co-product. This goes behind this inner cut out torus and then combines with the product again. So, and again, this is the result. But the result is Z and then 1 here. Again, you can ask, well, more explicitly, how can I describe this? And again, there is in this case a preferred basis. And for a full torus, the preferred basis is just of this form. Now here you need, you have two boundary components, which both are torus. They have opposite orientation, so you need one of those. This is often denoted by chi lambda for the torus. And the other one, due to the opposite orientation, would be denoted chi lambda minus t. And you can expand with respect to the basis given by the tensor product of these by gluing one from the inside, one from the outside. If you do that, you get the manifold S2 cross S1, and applying then to arrive gives you that this correlator can be written as a sum over lambda lambda prime. Certain coefficients, also called Z, typically Z lambda lambda prime, and then chi lambda t, chi lambda t, and lambda minus t. And these numbers that you get here are precisely the dimensions of these spaces that I have written down before. I said lambda lambda prime is a dimension of space of a bimodule morphisms of y lambda tensor plus a tensor minus y lambda prime. And now two comments. First, a lemma. If you look at this morphism, from A to A, this is an idempotent. And I invite you to check this statement graphically. From using this and some other simple results, one can show, well, first of all, it's clear by definition. No, first of all, one shows that you get this. Not only is this an idempotent, but also if you have your lambda and lambda prime like that, which is what you get when gluing these bases full cylinders. This is again idempotent simply because the proof that you use can be taken over more literally. You also can show that, so you have this result, and you can show that if you do these modular transformations of the torus, tau goes to -1 over tau, and tau goes to tau plus 1. Corresponding representation matrices commute with that. And the reason for this is simple. If you look at the picture of the graph that I have, if you do this modular transformation, this will be transformed in another graph. But a full Frobenius graph will always result again in a full Frobenius graph. And anyhow, you have to show that the choice of full Frobenius graph is irrelevant, which is not now. Side remark. And then this is enough for the examples. A side remark. Historically, in conformal field theory, people spend a lot of time to, given the category C, knowing what S and T are, by knowing what the characters are, classify all non-negative integral valued matrices Z, satisfying this, and the result is not nice, and there is no nice structure on it. And this is not a surprise, because not every matrix set which satisfies this is actually a partition function, torus partition function of a consistent conformity theory. Only if you can identify such an algebra such that you have this equality here. And there are many known examples where you can prove such an algebra. Finally, with an eye towards generalizations to beyond rational, all of this is rational, but with an eye towards generalizations beyond rational, at least to finite conformity theories, you could observe the following. You can talk about an object of boundary fields, which you get by just summing over all relevant labels, taking these spaces of fields with the given label, and tensoring this over C with the object y lambda. So this is an object in C. And similarly, let me just write it for bulk fields. For defect fields, and then bulk field is a generalization, a specialization. Bulk fields changing defect condition D to D prime. As now I have two chiral labels to sum over. I have this. So these are both A prime bimodules. So I have to take the space of a prime bimodular morphisms from y lambda tensor plus d tensor minus y, no, not lambda, mu prime, and then to b prime. This is by definition tensored over C with the object y lambda mu box times y mu prime in the tensor product of C with C rep, which remember is a braided equivalent to the Grinfeld center. And then you note that just like in the case of this particular object L, that was relevant for higher genus conformal blocks, these sums that you have here can be seen to correspond to a coend. Since time is over, I do not write this down, only coend sign. But then using the fact that vector spaces as functors are delta functions with respect to coends, you can get rid of that, and you add up precisely with the internal Hom for the module category M corresponding to A. Maybe I should write mod A for M and M prime. So this object of boundary fields is an internal Hom. And in the same way, here you can show, and this needs a bit more calculations, but not so much more, that this is can be written as the space of what is called internal natural transformations from between certain functors which are associated to these defect conditions, and natural transformations, internal natural transformations is the same as so these are functors from mod A to mod A prime, and then you have here M in mod A, and then here you have internal Homs in mod A prime of G of M, GD of M, GD prime. And details about this you find in a paper by myself and Christoph Schweigert, where we argue that in fact this is not just a rewriting that you can do for all finite conformal field theories, but that this is really the correct description of the object of defect and bulk fills and the object. Well, this is essentially known here, internal Homs for boundary. Okay, so altogether I was maybe 10 minutes late today, but that's still acceptable, I think. Okay, so that's all about conformal field theory. As far as correlators and topological field theory are concerned, I will say more about conformal field theory, but from a different perspective